Okay, get started. So you were supposed to kind of get back in the exponential function groove. It was a little bit of a flashback to kind of algebra days. How did the assignment go? You say easy? Good. What? Can we have a quiz on it? Am I hearing a request for a quiz? Whoa. So I take it it went pretty well, huh? Yeah, never mind, but while my classmates slay me. Yeah. You got a few dirty looks there. Okay. Are there any you want to go through from the assignment? Yes. 13 or 17, did you say? Let's see, 17 says what? Oh, 13? Okay. Yes, solve the equation. 1 minus 3, 1/3. This is number 17. Oh. We switched. Okay, we have 1/3 the quantity taken to the x minus 1 power, and that's equal to, if I can find it, 27. Yeah. Well, the thing to do here is try to get both. The only way you can get an exponent the only way you can get that x out of the exponent is to get both sides expressed to the same base. The key here is 3. Really, this is 3 to the negative 1. Isn't that another way to write 1/3? And this is, and then we can rewrite the left side this way. So I'll just stop and make sure everybody, do you see how I got there? Okay, first I rewrote 1/3 as 3 to the negative 1 power. Then I use the old exponential law. If you take a power of a power, keep the base, and multiply the exponents. So then I multiplied negative 1 times x minus 1. Okay? And now, if two expressions are equal and the bases are equal, then the exponents have to be. So now, therefore, negative x plus 1 equals 3, and then you can wrap it up. So therefore, and then let's just double check if that's right. Negative 2 minus 1 is negative 3. Is it true that 1/3 to the negative 3 power is 27? Yeah, the negative flips it over, 3, and then 3 cubed. So it checks. And I didn't go through any like that last time, so I'm glad you asked about it. Did you want to look at 17 too? No? 17? A little different. It says solve the equation for x. Let's just do that one over here. Okay, we've got x to the 3/4 equals 8. Yeah, what's different about this one is x is not in the exponent. So this is a totally different technique. X is down where we like it to be on the baseline, but I would like to get rid of that 3/4 power. I say get rid of it. That maybe is a bad word, because you can't just annihilate it. What can you do to it to make it into an exponent of 1? Because if it's an exponent of 1, isn't it really gone? Oh, the answer is we could take that, and couldn't we raise it to the 4/3 power? Of course, we can't just do that willy-nilly unless we also do it to the right side. Now this really is x to the 1, or x, just like we wanted it to be. Now, what in the world do we do to that? Well, you can either take 8 to the 4th power and then take the cube root of the answer, or you can first take the cube root of 8 and take the answer and take it to the 4th. It's a lot easier if you do the root first. The cube root of 8 is 2, and then 2 to the 4th power is 16. So yeah, I'm glad you brought both of those up because they're both, I'm sure you've done that before, but probably quite a while ago. Okay, let's look at, I kind of spilled the beans yesterday. I have a tendency to do that. I get so excited about stuff coming up that I can't keep it in. You know, I just leak what you're going to get for Christmas kind of type of thing. So anyway, it's too much fun, too much trouble. I never used to be that way. I guess I'm just getting older and less disciplined or something. I don't know. You know, all kinds of problems. I'm drinking too much. I can't keep secrets. It's not good.
Not bad.
I know the feeling. Who said that? Okay. You may have some of that feeling, but you don't have the age yet. It's called deterioration. But anyway, here we go. Do you remember we looked at something like, I'm sorry, that's my fault for leading you astray. But do you remember yesterday when we looked at something that was just like this? There's this fraction, 1 over 1 plus n, and we take it to the nth power. Now, of course, n has to stay the same. And then I think we started exploring different values for n. See, part of my ink got destroyed here, but if we plug in a 1, you get 1 plus 1, which is 2 to the 1st, which is 2. If you plug in a 2, 1 plus 1/2 is 1.5. And then when you take 1.5 to the 2 power, that's like 3/2 squared, which is 9/4, 2.25. Anyway, I ran a number of them through, and here's what the numbers come out to. And you notice that it starts leveling off. Do you see that? I mean, notice this number is not changing a great deal down here. 2.70, 2.71, 2.72. And then last time I think I had you look up E on your calculators. How did I do it? I said, you know, you got an e to the x function on your calculator, and I said find e to the x of 1. And you guys were telling me it's 2.718, something like, it was one of those. Okay, now, so we're headed at this e. Well, let me jump ahead. Here's really what that was saying. If you keep going with n and keep getting it bigger and bigger and bigger, the number you're actually heading at is e. And that's the e that's on your calculator. It's called the natural logarithm base. There's another one on your calculator called just log, and that's the common log. That's base 10. And you know, our whole number system is based on base 10. Even the metric system is all based on base 10. And it's one of the things that makes the number system so incredibly versatile, that it's based on 10 and you can just tack a 0 on when you want to go up another dimension. That's pretty cool. For natural growth, this one, the natural logarithm base, e, even though it's not very convenient, you can't write it all down very easily, is actually better. And one way to illustrate that is to talk about compounding interest. Here's actually how you can take a look at compounding interest. If you compound yearly, by the way, do you notice something familiar over on the right? 1 plus 1 over something to the, doesn't that look just like that 1 plus 1 over n to the nth? It's the same number, only, so we're getting the same answers here. What happens when you plug in n of 1? You get 2. What happens when you plug in n of 2? You get 2 1/4. And it's just like the previous page. Well, what's cool is it's showing you that this fits how you compound interest. And the more often you compound it, this number goes up. And guess what it approaches again? This is the only difference is instead of me going to 10,000, this time I did it. Look at, we did quarterly, monthly, weekly, daily, hourly, by the minute, by the second. And you notice we're getting really close to that E number again. And if we went to infinity, we'd be at E. Okay, so the best way to have money grow is to use the base E. I mean, if they call that compounded continuously. And banks will offer that in certain accounts. And that's the best kind of compounded interest you can't do better than that. That's like perfect compounding. Okay. I just thought I'd throw this out too. There is actually a infinite series that will give you E2. It's unique in that way. If you just you should notice a pattern here in these fractions. And if you keep picking, do this forever, add them up, you will arrive exactly at E. Of course, you can't do anything forever, but there's another way to find E. And there I've got, what, the first, I don't know how many digits of E. All right. The way to calculate compound interest continuously is to use this. Oh, I got to show you one thing before I do that. Look at this formula and then compare that to the one in the book on page 264, because I want to show you that they're different. And, well, they are and they aren't. They don't look the same at all. What's going on? The one in the book says 1 plus x to the 1 over x power, and the limit of that as x approaches 0 is E. Mine, I don't have 1 plus x. I've got 1 plus 1 over x to the x power. So, and they've got 1 over x power. I've got x, you see the difference there. And my limit doesn't go to 0. Mine goes to infinity. Well, what is there really any difference? What's going to happen to 1 over n as n goes to infinity? What's going to happen just to this part? 1 divided by infinity? That's heading for 0, right? Okay, now look in the book. As x goes to 0, what's the second part of their parentheses going to go to? X goes to 0. It's the same deal. Anyway, and then why? Yeah. Because this is flipped upside down, you'll notice their exponent is flipped upside down. I like this form a little better because it fits the financial model better, but they really are saying the same thing. So I just wanted to point out to you, so you don't go look at your book and go, what in the world was he showing us when this seems to be so different? All right, now back where we were. We were talking about calculating compound interest. If it's compounded perfectly, this is the formula you need. P stands for the principal. That's the amount of money you put in there to begin with. R stands for the interest rate. E is that number we've been talking about. And A is just how much you're going to have in the bank, the amount, I guess, stands for amount. So A is how much you're going to end up with. Now, yeah, and you'll see this in your book. At the bottom, yeah, I guess we should put one more thing in there. And then it kind of becomes PERT, if you want to remember, T is. So if you look at the bottom of page 266, you'll see two formulas. This is the first one. And that's kind of in its simplified form. Before, I mean, that only works when it's compounded continuously. But this one, right above it, is when you don't know, when you want it to be able to handle different kinds of compounding. So let's talk about the letters here. We already did the top one. Principal, rate, time in years, amount of money you'll have left. Same thing here. Principal, interest rate, time in years. Now, N is new. N is the number of times per year that it's compounded. Where do they ever say that here in the book? They don't, do they? How can they not talk about that? Well, they kind of do up higher in the page. Do you see the table higher up on page 266? Look at when they do compounding annually, then N is 1. When you do it semi-annually, N is 2. So it's the number of times you compound the interest per year. When you compound monthly, then N is 12. So N stands for number of times compounded per year. So you really need to be able to make use of, you need these two formulas. The bottom one will work for any compounding, but if you want to do continuous, we can simplify this because does anything here look familiar from the previous slides? Now, doesn't that 1 plus fraction to the to the n power, does this look familiar? It should. It's that e guy. And so what happens is part of this dissolves into e, and this actually turns out to be a lot easier to remember this way. Now, in natural growth, like bacteria growth, population growth, you get pretty much an e growth. And so we'll be using an equation that looks more like this most of the time. For money, though, this one at least gives you the option to compound a different number of times per year. Okay. Yeah, and you remember yesterday I made a claim. I don't know if this demo is the best, but we're going to show it. I've got a link here to a Java applet that helps. It's not perfect, but it shows how the height of a E graph is always the same as its slope. Okay, so here's the deal. Right now, this blue graph is the graph of y equals a to the x power. That's the creature we were talking about yesterday. Right at the moment, a is 1.5. And if you click on this, you can increase a. You notice how now a is 1.6. You'll see the graph change. By the way, this is just the identity function that goes through 1. So the 45-degree angle line. And why do we need to go through 1? Do you remember yesterday? What was true of all of our exponential graphs yesterday? I had a bunch that went like this, at different slopes, and then we had some that did the opposite. But didn't they all go through the point 0, 1? Remember that? Why? Because anything to the 0 power is 1. So this point is important. And so if you're wondering why do they have that red line going through there, that's why. They have to start with that value. Now, as I keep increasing a, you notice the graph gets a little bit steeper. We're up to 2.3. It goes up by tenths. And then it stops at e. Now it's e to the x. And this is the perfect graph even though I guess this isn't demonstrating that greatly. But right at 1, the slope of the curve is 1. Can you at least see that at this point the red line is tangent to the graph? Right at the point. Now, if we went to 2, which we can do right here, at this point, if we drew a tangent line, its slope would be, I'm sorry, right here, the height is 2. Right here, the tangent to that curve at that point would have a slope of exactly 2. And on this graph, if we go up to the height of 3, the slope there will be exactly 3. This is the only graph that does this, okay? E to the x is the only graph that always has the same slope as its height. And that's why it's so fantastic for calculus, because its derivative is itself. It's kind of like it's its own derivative. Kind of a weird thing from years ago. There used to be a real crazy song, was popular for about a week. It was all about it was humorous, and it was all about complicated relationships and, you know, second cousin, three times removed and things like that. And anyway, the name of the song was "I Am My Own Grandma." Okay, which obviously he wasn't, but you get the idea. Well, this E can say, "I am my own derivative." It's a new song coming out. You watch for it. You heard it first here. Yeah. Sorry, but it is cool because, again, I jumped the gun. Now I went ahead and did it. I went ahead and told you some things from the next class. But sorry. Let's get rid of this and let's go back. Okay. E also shows up in another interesting place. Do you see e to some certain fractional powers in this graph up here? Well, if you look at the equation at the top, do you see how it says e to the, and it's got these 2 fractional powers? This is that's the red curve up there. That's kind of a, well, it's all of these curves. That's a famous curve called a catenary. I don't know if you've ever heard of a catenary, but it's basically if you take anything flexible like a rope or a chain and hang it from the 2 ends, it will form a catenary. It's really close to a parabola, but not quite. So a parabola is based on gravity, and if you hung cables straight down from your cable, then it would be a parabola. Like, for example, the Golden Gate Bridge has these nice big cables coming down. From each of those big cables, there are vertical strands. Well, then it's not a catenary. But if you let it hang freely in its own weight, as you can see on the left, a chain or a rope or whatever, then that forms a catenary. And the reason I've got the St. Louis Arch on there is because the St. Louis Arch is an inverted catenary. That's how it was designed. Anyway, obviously this is a big deal in creation because there are things that hang, like simple things like strands of silk in a spider silk, in a web, are little catenaries. And if you're going to build buildings that have some kind of suspension in them, you would need to know this. So for engineering purposes. So anyway, E shows up there too. Okay, let's take a look at some assignments, some sample problems. And by the way, there are some catenaries. I was just talking about catenaries. I believe those are catenaries when you go to numbers 27, 28, 29, and 30. They ask you to plot those. Don't be surprised if you get something that looks chain-like, like that. Anyway, 1 through 4. Use the properties of exponents to simplify. Let's do number 2. Now, this is all review. How do you simplify 2a? 1 over e, parentheses, to the negative 2 power. What's a simpler way to write that same thing? Well, you're right about it. 1 over e, what does the negative part of the exponent do? It flips it right side up and it becomes e over 1 or just plain e. And then what's still left? The 2, right? So wouldn't it just be e squared? And how about d? You could flip it right away, or, yeah, and then that's it. But I don't think you'd want to leave it like that either, because then it'd be e to the 2 over e to the 5, and can't you simplify that? What's e to the 2 over e to the 5? Be careful. E to the 2 over e to the 5. It's e to the third, but where's the e to the third? On the bottom. So 1 over e to the third. Okay. What's another way we could have done that? Couldn't we have first simplified the parentheses? What's e to the 5th over e to the 2? Well, that's e cubed. And then what's e cubed to the negative 1 power? 1 over e cubed. We come to the same answer. 2c. What's that one? 2c. E squared. E squared. Correct. What's a simpler way to write 2d? Wouldn't it be simpler just to write e cubed?
Yeah.
Because now we don't have that negative power, we don't have a denominator. Let me know if I just puzzled you with something.
Why do you, like in 2a, why do you just flip it so it's e?
Because of that's what the negative, what does the negative part of the exponent mean?
Oh, okay.
So that negative tells you do the reciprocal.
Okay.
That's why flip. So that's your sign. I gotta take the reciprocal. How about 4? What's a simpler answer for 4a? Well, let me ask you, first of all, let me ask you a question that gets you ready for that. I know you know this, but when you have something to a power and then you raise it to another power, what's the technique you've learned in the past for doing that? So like, something to a power to another power. You keep the base and you multiply the exponents. When do you add the exponents? Like if you were doing e squared times e cubed, that really is e to the 5th. There you add. So when you're multiplying two numbers with the same base, then you keep the base and add the exponents. But what do you do when you take a power and raise it to another power? Keep the base and multiply the exponents. Okay, so with that in mind, what's the answer to 3a? 4a. 1 over e squared, or first of all, wouldn't it be e to the negative 2? And then we don't want to usually leave a negative exponent, so we would write that as 1 over e squared. How about 4b? What's that equal to? By the way, actually none of these are dependent on the letter e, are they? It could be j, couldn't it? I mean, it has nothing to do with e at the moment. None of the things I've been asking you to do. So anyway, back to 4b. How do you handle two numbers with the same base and they're being divided? Keep the base and subtract the exponents. Now be careful, because you're going to have to do 4 minus a negative 1/2. What's 4 minus a negative 1/2? 4.5. And how would you write that? You're probably not going to write e to the 4.5 power. You're going to write, yeah, e to the 9 over 2 power. Very good. Notice how Steve takes all the credit here. Is that you? Who said thank you? Oh, okay, that's all right. It came from that corner.
Wow.
Oh, boy. All my friends. Sorry, Steve. Well, a little earlier you said, yep. Yeah, you got it. Okay, on we go. How about for Steve? Steve, why don't you take that one? Oh, you can do it.
You serious?
Yeah, go ahead. I mean, it's not bad. Sure you do. Power of a power, keep the base, and multiply the exponent. Okay, now what's negative 2 times negative 4, Steve?
Huh?
What's negative 2 times negative 4?
8.
Yes. So now you got it. C to the 8.
Oh,
Okay, 4D. 4D, that doesn't have to be C, or maybe it should be. But anyway, how about 4D? Now, this is different in that what? We're taking two exponential numbers and multiplying them. The shortcut says keep the base and add the exponents. So now you got in your head, think what's negative 4 plus negative 3 halves? Well, negative 3 halves is negative 1 1/2. So what's negative 4 plus negative 1 1/2? Negative 5 1/2, which we could write as 11 over 2. So e to the negative 11 over 2 power, or 1 over e to the 11 over 2 power. Okay, see, all those things are important for what we're about to do, but they go back. Let's do some equations. Next section. Solve for x. These are kind of like the ones Katie asked about earlier, and they're good for us to go through. Let's take number 6. How in the world could we solve for x on that? Well, I don't know the best way to answer. There are two ways I could give you a clue on this. One is, you may not get this, but couldn't I write both sides as e to some power? E to the what power is 1? That's it. Now, since those are both equal and the bases are equal, doesn't that mean, therefore, can you see that? The other way I could have explained it is just what's the only power that when you take a base to it always comes out as 1? So it's 0. Yeah. Okay. Let's go on. Number 10, x squared over 2 equals e. It's supposed to be e squared. Thank you. Okay. Well, how are we going to solve for x? This one's more traditional algebra. Couldn't we multiply both sides by 2? Okay. Now we got to get to x. So can't we take the square root of both sides? I want to clearly point out that e is not under the square root sign, right? Because square root of e squared is e. Okay. How about that one doesn't look very hard. I guess that's good enough for that section. Let's go to another one. Match the match the function to its graph. How are you going to do this? Graph it and just see which one matches. Yes, you could. Okay. Another thing you might do, if you didn't have a calculator right at your fingertips, is you could look for a few key points. For example, look at number 13. ask yourself, what would that thing be equal to if x was 0? Well, just quick do it. In the exponent, if x is 0, then that becomes e to the first, right? And how big is e? About 2.7. Okay, now which graph has the point 0, 2.7-ish on it? I only see one. You see it? Yeah, because one guy who identified it, isn't it graph F? Okay, so that kind of thing, the old process of elimination could also be used. How about this? Yeah, how about 15? E to the x squared. Okay, now again, what if x was 0? Well, 0 squared is 0, and what's e to the 0? 1. Okay, so this graph goes through 0, 1, but I think there's a number of them that do that. There are 3 of them. Okay, so let's go one more step. What if x is 1? Well, what's 1 squared? 1, and what's e to the first? E. Okay, so at 1, it should be up to 2.7. I see 2 graphs that might, no, I think we're down, now I think we know which one it is. C or D anyway. Yeah, I guess it's 2. We're down to C and D. But now, here's the kicker. What about x equals negative 1? Well, what's negative 1 squared? 1. And what's e to the first? E. So that's 2.7. So now, which graph has the point negative 1, 2.7? Now we're definitely down to D. So anyway, you could use this little, take some easy points, and you can kind of eliminate fairly quickly. Okay. Next section, sketch the graph. Okay, now before we do those, I want to make one sketch up here ahead of time. Let me pull up a graph here. Okay, what I want to do is graph, first of all, kind of the one we've been talking about all day today, y equals e to the x. Now, first of all, tell me, what famous point should this graph go through? 0, 1. So let's just put a dot there right now. If x is 1, what should y be? 2.7. So if x is 1, I don't know, it's somewhere in there. And so anyway, this thing looks something like this. And we know it has that same exponential look to it. Now, what they're asking you about in this next section is, what if we duke around a little bit with the exponent? So in the first one, number 19, they say, what if we say e to the x minus 2 power? So here's what they, I want to put that in a different color or something. So here's what they're asking you in that one. Now, without making this too painful, doesn't that mean that every x that you pick will now be, before you calculate, you have to subtract 2 from it. Okay, well, for example, let's just take the easy one. What if x is, let's say x is 3. If x is 3, what's going to happen? What's 3 minus 2? And what's e to the first? So at can you see what happened? The graph is exactly shifted 2 units to the, I should do another one. What happens at x equals 2? 2 minus 2 is 0. E to the 0 is 1. So Can you see how all these points are literally shoved to the right too? So I don't know what you remember from your algebra class, but you remember whenever we did an x minus something, that meant the graph was laterally shifted? Ask yourself this question. What would you have to do to get this back to 0? Answer, it would have to add 2. So therefore, that thing is shifted 2 to the right. So now you could sketch the graph, and you don't have to go through any more points. You just kind of take that same graph and you would just show that it's the same graph shifted to the right. Okay, so that's not too bad. But now we got something else going on. What do you think is going to happen in number 20? We're going to take the exponent and multiply it by 2. So like if x is 0, well, that's going to be the same, right? Because what's 0 times 2? Still 0. And e to the 0 power is 1. But what about at x equals 1? I'll tell you what, I'll do blue on this one. Okay, so at x equals 0, we're going to be at the same place, right here. I'll put the dot right on top of the old one. Now what about x equals 1? Well, 2 times 1 is 2. And what's e squared? I don't know, whatever 2.7 squared is. It's probably about 7-ish or something like that. You can check it for me. So now, instead of only being up at 2.7, somebody do it yet? Thank you. So I'm somewhere up here. So the curve starts, it goes through the same point down here, but it's going to be quite a bit steeper. As you can see, it's heading uphill a lot quicker. Now, I know you're going to look at this and go, looks to me like we did the same thing. That's the trouble. Going up quicker can sometimes look an awful lot like just shifting it to the left. But I would like you to, that this shouldn't just be thought of as a shift to the left. In fact, it can't be thought of as a shift to the left because aren't these 2 points in the same spot? So for a shift, all the points have to be moved over, and that clearly didn't happen here. You can tell my blue spot is supposed to be right on top of that black one. Anyway, look for some patterns here. Don't just do your graphic calculator thing. What's going to happen when you put a negative sign in front of the x? Like on 22. What happens when you... Well, what does a negative sign mean in exponent, first of all? Reciprocal, right? So now, any number you would have gotten before, like 2.7, would now be 1 over 2.7. And it's going to be dinky. It's going to start getting smaller. And if you take, like, to the negative 2 power, now it's 1 over e squared, 1 over 7.3. And it's getting smaller and smaller. So anyway, you're going to have a totally different shape. Then there's a couple graphing utility things from 23 through 30. You're going to see some catenaries in there. And then you can see some kind of growth problems in 23 through 26. Then we have some money growth problems, compound interest. What are you going to do to solve those? If they ask you to compound a certain amount, then you're going to use that guy on the bottom. If they ask you to do compounded continuously, then you're going to use that guy on the top. Okay, let me see. Let me see what I got up on the for assignment. Whoops, wrong calculus. Now, I'm going to modify that a little bit. So here's what we're going to go with. Let's go with 1 to 37, and let's do every other. Again, every other odd. Okay, so 1, 5, 9, ... 37. Okay. Thanks. Have a good Thursday.